Okay, so with the prerequisites now, we would like to delve into Yang reduction. And so we recall that that what Shane and Yao did was to almost anyway was to, well, let's quote unquote say deform it down into the Riemannian setting. So not perfectly like that, but we'll get to that soon. So we solved the Yang equation, which in coordinates looks like this, where we extend K, this symmetric CO2 tensor, trivially up into M cross R here, so that it acts trivially whenever you plug in a time derivative, T derivative, and then this expression traced here is nothing but the trace. This is the second fundamental form induced here on the graph, and then we trace it. So this is nothing but the mean curvature of the graph. And of course, everything, the coordinates that we work on the graph with is the ones that we inherit via the projection diffeomorphism from M here. And so so we want to solve for a function J of f equals 0. This is Yang equation, and so we denote by M hat the graph of this. And we hope now that somehow this will take us down into Riemannian setting or sufficiently close. And just to, so again, we're working with so we say that we have now asymptotically hyperboloidal. We want to prove a positive mass theorem now. So we want to do, we assume that our initial data is asymptotically hyperboloidal. I won't skip back to that slide here because this is now turning into a YouTube video, so you can just recheck that yourself. The metric converges to the hyperbolic metric, and the second fundamental form converges to the hyperbolic metric. Yes, I'm sorry. Right. Yeah. So now let's see. Well, yes. So the nice example here is when we think of the function f of r square with 1 plus r square. Now, and if we plug this into Yang's equation, and that's a nice little exercise if you want to, that's an analytical solution. If the initial data that we work with is identically the hyperbolic space, hyperboloidal space, where K is this is that when we are umbilic, and the induced metric on the graph, moreover. So it's not to. So I mentioned before that the induced metric on the graph in that product with that metric is G plus the F tensor with itself. So F is spherically symmetric, so it has no tangential derivatives. So the other components are just the same, but the RR component here, again, of course, we work with we assume we have polar coordinates for the initial data, and so the metric is simply the following, and so this is 1. So in particular, the induced metric on the graph is identically Euclidean space. So this is now very promising, because that means that we could hope to deform what is initially an asymptotically hyperbolic data down into the asymptotically flat setting, and see where things go. And and this motivates the following. I'm getting ahead of myself. So so this motivates that we can expect the solution to be an asymptotically Euclidean graph, and the asymptotic behavior of the function would be 1 plus r squared. So this is still a bit in contradiction to what Shane and Yao and Eichmeier obtained in the flat setting, where the Yang graph tends to 0. Let me simply now define what is called Wang's asymptotics. So I did mention that Jiadong Wang proved the positive mass theorem for the asymptotically hyperboloidal setting in 2001, 20 years ago. and here the specific type of asymptotics for the initial data. So we simply say here that the push forward metric is the hyperbolic metric, these two, but we have correction terms here that acts that lives the m and this order term here lives on the sphere as 0 to 10 symmetric 0 to tensors, and similarly this is the case as follows. So combined with this, there is a density theorem proven by Anna Sakovic and Matthias Dahl, 2015, that tells us that we can approximate asymptotically hyperbolic initial data, the general initial data with Wang's asymptotics, such that for any of these functions, recall that we defined the mass vector in terms of these n+1 dimensional vector space of functions, and the mass vector components are close, so that we can then so we approximate with Wang's asymptotics, and in particular, if you have a dominant energy condition satisfied here, which we, by the way, of course, will assume here too, then this will be strict on this initial data set now. So henceforth we can have in mind that we have initial data that has Wang's asymptotics, and that the dominant energy condition is strict. So suppose then that we would like to solve Yang's equation over asymptotically hyperbolic initial data with Wang's asymptotics. Then if we plug in, and recall that of course this square root, this was an analytical solution when the initial data was identically hyperboloidal space. So if we plug in the following function into the Yang equation, and we require that the terms decaying slower than 1 over r to n plus epsilon here vanish, then we get the following expression, that this is a PD that must be satisfied on the unit sphere. Alpha here are functions, and psi are real valued functions on the unit sphere. So one finds that psi must be constant, and moreover alpha must satisfy this, or p and m are something that is part of the data. Now the first term here is this term here is negative, so Fredholm alternative gives a unique solution for each right-hand side. And if we skip, let's assume for simplicity that everything is smooth, the initial data and everything in the metric and so on is smooth. So we have a smooth solution alpha by standard elliptic regularity. So we have a solution alpha, and so we can expect. So this is heuristically we can heuristically then expect that the solution will behave like this in the infinity, and this could help us to create barriers which would then control asymptotically the function. So I didn't mention this before, but one of the things that Shane and Yao did when they solved the Yang equation was that a couple of a priori assertions about the Yang graph before it was solved. One of them was the control at infinity of the functions with barriers. That is to say, if we go to this slide, so they had explicit integral functions where that served as sub and super solutions. So f plus and f minus of any Yang equation solution, so that f plus would lie above and here f minus below, but they still had the same asymptotics at infinity. So one that could control the asymptotics outside of a compact set here. And the same thing we can do in this setting with Wang asymptotics. Of course, again, the barriers will go up like the square root 1 plus r square function with this asymptotics. But to be more rigorous here, just to mention that we say that they are upper and lower barriers if they don't solve the Yang equation, but if they are super and sub solutions with this and that there is some R naught here, so that the radial derivative diverges in the negative and positive infinity like this, like indicated in the picture here. So we can assume R naught is outside of this compact set in the so that we do this again. We can think that we are down in the chart at infinity and R minus the ball. So R naught is something which is very big and outside the ball, and so we have this upper and lower barrier for the function. So this gives us control over the asymptotic behavior of the function, and I believe it is called the Bernstein trick to show that f is squeezed in between here. So in particular, if we now this is also a rather lengthy and technical calculation, so I will not say more than simply briefly that so we get this asymptotics as expected above. And just to mention how this is done then, so one starts with an ansatz that f is this again some function which depends only on r, and then alpha dependent was angular dependent in general, and so there is a change of variables that one can do, namely the following, and one can plug this into the Yang equation and get one estimates it from above and below, and estimates any angular dependent term, and so that we end up with basically an ODE, and that we can solve, and so we recover the k plus and k minus then for sub and super solutions, and in turn we recover f plus and f minus from this, and alpha is like we had in the previous slide. So and in particular, if the initial data has spherical symmetry, this is sufficient to solve Yang's equation identically using ODE methods. And a nice example of that could, for instance, be an example taken from an article by Bryden, Puri, and Somani recently, where this is done over the Schwarzschild. But okay, so with that we have control asymptotically over the Yang graph, although we still haven't solved anything explicitly. So we would like to solve the Yang equation now, so there is, however, a little problem with that, and so we would like to do the continuity method here, and I'll explain that in the next slide if you haven't seen that. But the problem with the continuity method is that we need zero terms involving no derivative on f. So if you check, the Yang equation contains only first and second derivatives on f, but no term that is only f. So it's not possible to obtain certain a priori estimates of the function that one needs in order to do the continuity method for a solution. But and this is not only a technical obstruction, but in fact the fundamental aspect of the Yang equation, as we will see now in a few slides. But so and this so what we do is we solve the regularized Yang equation, and we solve it on compact balls. So, and this is also of course traces back to Shane and Yao, where one takes tau to be small and positive parameter, and one solves not j of f equals 0, but j of f equals tau times f, and then in the long run one wants to tau go to 0. Now on the one hand, So the right hand side will be will not be globally bounded by the barrier asymptotics that we found in before, but the left hand side so we want, but the left hand side is bound, so we want to solve this on compact sets here. So for instance, coordinate balls, and so just let me briefly describe how this is done. So the continuity method, and so we write Yang's equation into this form. Again, the Yang equation on the left hand side equal tau on the right hand side times the function. But we parameterize this now with some parameter s, which is in this interval here, and we solve it on some big coordinate ball. And we take it as a Dirichlet problem. Now, in the asymptotically flat setting, one would set the boundary here to be 0, but recall that here we go to infinity at 0, so we have to make some boundary function here, and that we can, for instance, take to be the average of the barriers. And then we simply check what kind of what parameters little s here that we have a solution for. And we can show that script s here as a subset of this interval is on the, so this, and the continuity method then says that you want to show this is non-empty and open and closed, so it must be the entire interval. And of course, when s is 1 here, this is just the Yang equation and the problem that we want to solve. Now, to plug in s equals 0 here, it is not difficult to see that the trivial solution will solve this, of course. And to show openness, one can consider a certain operator where one maps functions C2 alpha functions, or we can take this well, C2 alpha functions, for instance, or better regularity, and values of s, and one can do an implicit function theorem argument, and standard PD theory will tell us that one can linearize this operator, and then the linearization of this operator is invertible. And so the implicit function theorem tells us that we have a function f for each given s here, and one can so that gives us openness. And to show closedness of script s, then we take simply convergent sequences, and it is possible to find using elliptic regularity, among other things, to show that there are convergent subsequences that converge to the solution. So using the RCL-Ascoli theorem. So this is both open and closed and non-empty, and so must equal 0 to 1, and s equal 1 is the regularized Jang problem that we wanted to solve. So, assuming then that we have that, we would like to take the limits r goes to infinity and tau goes to 0. And this was done historically in the flat setting then separately. However, here we cannot really do that because the left-hand side is bounded, whereas the right-hand side is not. I mentioned, of course, that f goes as square root 1 plus r squared. So globally on the initial data, one cannot expect this equation to have a solution. So we have to take the limit simultaneously. And this we do with geometric measure theory methods. And I do not go too far into this here either. This is, but I would like to say a few words about it. So again, the graphs for each for tau. So we parameterize. We take a sequence where tau goes to 0 and r goes to infinity. And so the graphs will have bounded mean curvature. One can choose r and tau to go to their limits, so that the mean curvatures are bounded. And so one has this closed class of currents in GMT, in geometric measure theory, such that when you converge, there are compactness results so that you converge within this class, and with nice limit properties. And so one can do, to check regularity, one can do a blow up analysis, or so one talks about the regular set, which here means basically points in the manifold where we are locally C1 alpha regular, and then the complement of that in the graph is where the so-called the singular set, and the and one can show that when you zoom into that, you do a blow-up analysis. So if this had been sufficiently regular for a smooth manifold, this would be nothing but some kind of hyperplane. If you think about this as embedded into Nash embedded into Euclidean space, for instance, you can draw this to the origin and scale it up, and this is nothing but some hyperplane. But in the case of being in the singular set, this would correspond to a certain type of hypercone, that minimal stable hypercone that can that does not exist in these low dimensions. And so one has a regularity theory here for these currents in this class here, which script F here, script FC. And so that from that we know that the limit graph will be sufficiently regular here in these low dimensions, and this is why, of course, you get this strange result that n equal 4, 5, 6, and 7, but not above, because of this non-existence phenomenon. And one can also discuss. One can also show that you have smooth convergence, meaning, so you think pointwise on the limit graph that the graphs converge as smooth as functions, Hölder functions, really in norm over this tangent space into a function which is locally describing the limit graph. So this is what is meant by smooth convergence, and in particular, then of course the limit graph will solve a Yang equation. And again, this non-existence result happens in these dimensions, but the singular set would consist of isolated points if we have spatial dimension 7, so that and this can be circumvented too. So all in all, we have a Yang graph in dimension 4, 5, 6, and 7 that has these barriers. That solves Yang's equation that is squeezed in between these barriers at the infinity, so we have infinity control. But what can happen within this compact set, which is bounded by R0 from the previous lines, was that this is of course not bounded inside here, and when we can have these blow-ups and blow-downs. And so here we think we and furthermore so there could be only finitely many, of course, but if we push down the Yang graph infinitely much, then locally we will converge smoothly to the cylinder, which is here depicted as an R factor times some kind of closed and sufficiently smooth hypersurface in the initial data. And now, of course, the smooth convergence, from that one, we see that we inherit the Yang equation induced on these cylinders, but depending on to what extent, what the convention is, if you calculate the mean curvature with unit normal pointing upward or downward, the Yang equation induced on these guys will have a different sign of the mean curvature. So the cylinders, they will satisfy a Yang equation, but perhaps with a changed sign. So that is to say, mean curvature is equal to minus the trace of k or plus the trace of k, depending on which. And from the metric structure in these coordinates, it's moreover not difficult to see that this Yang equation must be satisfied by these base closed hypersurfaces here, called marginally outer trapped or inner trapped, depending on which direction you blow away. These ends here are called cylindrical ends. We refer to them as cylindrical ends, and this is an end, some asymptotic end too. So this is so with that we have solved Yang's equation over initial data with Wang's asymptotics.